Hello, everybody. Thank you for the introduction. My name is Paul Azunre, and I am a postdoctoral associate in the Research Laboratory of Electronics in Professor Mark Baldo's lab. I graduated in the year 2014 from this institute with a PhD, thank God. Today I will talk to you about globally optimal engineering system design. I will talk about class of algorithms that can guarantee that the results that they produce are the best that can ever be found, which compared to existing algorithms, what that means is our algorithms take the ambiguity out of the process of designing such systems and convert this process, which is often considered to be an art form, into a science. And we demonstrated this, the efficacy of these algorithms by applying them to the important problem of reducing reflection from a silicon solar panel. Okay, so as many of you know, optimization is at the core of many engineering challenges. So often an engineer wants to figure out which one of many options to achieve a certain goal, does so at the minimum possible cost. So an example that you are probably familiar with is the traveling salesman problem. You have a list of cities. You want to visit every city to deliver some load at each city. And you want to do this by covering the least distance so that you use less fuel. This is a popular problem. So existing algorithms to solve many of these problems have a problem. And the problem is that, well, the way they work is they start at some initial guess for the solution, and then they try to improve that with time. This is a schematic showing a genetic algorithm, and many of you have heard about them. The problem, and as you can see, a man is probably not the global optimum. A woman may be, but so here I try to show the same thing. So you start somewhere, and then you may get stuck in some local optimum, whereas there's something much better somewhere else. This is where our algorithms come in. We will always find this point. How do we do this? We focus on exact parallel deterministic global optimization methods, such as branch and bound. And the way these algorithms work is they exhaustively search the entire search space using massive amounts of computational power. And these ideas, they exhaustively search the whole space intelligently using massive amounts of computational power. These ideas are not new. They have been known for about half a century. However, it's only recently that advances have been made in certain areas that have advanced this from an obscure technique relegated to a few special applications to the mainstream. And to give you an example, any of you could go home today and run thousands of computers in parallel from your laptop. Today, that's commonplace. Microsoft does provide services to do this. Amazon provides services to do this. 10 years ago, this was not possible. So we think this places us at the place where we can make this widely accessible. To demonstrate this concept, right, we need to do it. We focused on the problem of thin film optics, which is a $10 billion market. This is where you try to figure out some sequence of layers to put on top of a substrate to modify the optical properties in some desired way. And the problem we personally cared about was how do we reduce reflection from a solar panel such that more light can go into the cell and the cell can become more efficient. And I'll give another example, which is kind of dramatic, but it helps to illustrate the point of how important this problem is. If you send a soldier to hide in enemy territory wearing camouflage, the only real way to find them for the enemy is to see light reflecting off the looking glass of their weapon. So as you may imagine, there are a lot of people who pay a lot of money to minimize reflection from glass. But let's return to the problem that I care about. But before I go on, I would like to mention that if you open a book, if you're not convinced and you open a book on designing a system like this, and you read through it, you will find that thought leaders in this field think that this is an art form. So design of engineering system is considered to be an art form by thought leaders. This should help illustrate that bringing such an algorithm into the mainstream could lead to a real paradigm shift. Back to the problem that we solved, reducing reflection from a solar panel. I show here a transmission electron microscopy image of the sequence of layers that our algorithm spat out. And also, visually, I hope you can see that this piece of silicon is completely black. So all the light that falls on it goes in. And here's the same data, but more rigorously. Normal incidence reflection from a solar panel. In blue, we have a reflection from one of the current state-of-the-art technologies. It's a polycrystalline silicon solar cell. 18% reflection on average. This is our solution in red and black, about 2%. So that's 16% improvement in reflection absolute. And if we convert this into power conversion efficiency improvement, this is a 2 to 3% improvement, absolute improvement in power conversion efficiency of solar energy, which is a huge deal because even 1% turns heads, right? This is 2 to 3. Of course, solar energy and optics is not the only place where people are interested in optimizing things. So you can think about drug design, there are problems there. Lens systems, that's optical, I guess, routing, semiconductors, the list goes on and on. We hope to spend the next couple years exploring the optics and the solar and continue our expansion into other problem classes with time. There are a number of business models we are considering, depending on what the customer needs, whether you need software consulting or you need engineering consulting or you want software as a service, you just want access to our engine. So depending on what you need, we can probably do it for you. If some ideas are stirring in your head about some problem you want to optimize, please come talk to us at our poster, and let's optimize your product. Finally, I would like to thank all the various people who've contributed to this project over the many years we've been doing this. And of course, thank the Deshpande Center for all the support, the money, the exposure. We've loved working with you. Thank you.